All right, good morning, everybody. Let's see the last portion of this chapter. So, let me just find my pen. Oh, there it is. So, last time we talked about what the definite integral a to b f of x, what that represents. It represents not necessarily the area that we might be interested in, but instead it represents the net area, or we can also call it the signed area between the graph f of x and the x-axis. So that means that if I have a graph, oops, let's draw a straight line. And the graph over my interval, let's say A is over here and B is over there. That is the graph corresponding to the function. It's going to associate a positive sign to areas above the x-axis and a negative sign to areas below the x-axis. And if I do the definite integral all at once, a cancellation occurs and I don't actually get the total area that I want. Instead, I need to break it up. For the total area, I need to look at A to C, where C is an x-intercept, and then C to B, and I need to look at them separately and then make them all positive and add up those pieces. I have to sort of fix this issue manually. What's built into the definite integral can't be avoided. I just need to be aware of it. So we've done some examples on this, and you're welcome to do more. I think we've done enough, but we can do one more. Let's, for example, say, just pick an easy one. Let's just pick number 12. Where's 12? No, this one. Just to make it easy, in the case where I can graph it and visualize what's happening. So I have 4 minus x squared on 0 to 3. What was that number? 12. So my function is 4 minus x squared on 0 to 3. Now I can graph that. To help me visualize what's happening, but in some cases, graphing it might be too much effort, and that's not the point. In this case, this is just a couple of transformations on my basic parabola, shifting my parabola up over here. A little wobbly, but there we go, at 4. And my interval is 0 to 3. Let's just put 3 over here. And I see that I have some parts of the area above and some parts of the area below. So I need to find the x-intercept, whether I graphed it and can see that this is happening or not, I need to find the x-intercept. That is setting y equal to 0, solving for x. I get x equal to plus minus 2. So that means this guy is sitting in my interval. X equal to 2 is in the interval that they give me. I don't care about those that are not in the interval. That's completely irrelevant to me to calculate this area. So that then tells me I need to calculate two integrals from 0 to 2 of the function and from 2 to 3. If my graph is correct, the first one is going to be a positive area, the second one's going to be a negative area. But even if I don't see the graph, because the function might be too complicated for me to worry about that, some of these answers are going to be negative and some of these are going to be positive, which just confirms the fact that I have to split them up to avoid that calculation, that cancellation, if the calculation is done all at once. So my antiderivative is the same every time. It's going to be 4 times x minus x cubed with a 1/3 in front, and I'm going from 0 to 2 on this. Same antiderivative, so even though I have two integrals, the antiderivative work is the same. I just have different numbers to put in. So we'll get an answer for each of these, plugging in a 2 minus plugging in a 0. But luckily the 0 makes the calculation super simple, because that second bracket that I'm going to plug in 0 for, the whole thing is just going to be 0. So let's see what we get when we calculate the first one. I get 5.33 if I round it to 2 decimal places. And for the second one, I will just emphasize once again, for those that need it, that I'm plugging in the top boundary value, and then I'm subtracting all of the answer that I'm getting when I'm plugging in the bottom boundary value. Just to emphasize. We'll do it all in one go, but you can certainly break it up into pieces if you want to. Now I already know what this second bracket is. Whoops. Because when I plug in a 2, it's the same as the second bracket. So my answer is negative 2.33. And you see, as we suspected, some of this is positive, some of this total area that I'm looking for is negative. So then I can go and say, let's ignore those negatives. The total area is 5.33 plus 2.33 for a total of 7.6. Well, if I use the original numbers, it's going to be 6.7 because it's 6 repeating, and I always have to use the originals when I do a future calculation, even though my presentation has them repeat. So rounding issues aside, I just have to split it up according to the x-intercept. Whether I can see the graph or not, when I'm looking for total area, I need to be aware that this positive-negative area calculation will cancel pieces in my definite integral if I do it all at once. So I need to manually go and separate them. All right. So the last topic is when we want to find the area between two graphs. If we now step it up a little bit and say our boundary doesn't have one curvy line in it, but maybe two, we can visualize that like the following. We can say, well, let's suppose I have some graph up here coming from a function, and I have another graph up down here coming from a different function. Let's call it g, and I'm interested in the area between a and b. So I'm interested in this area over here, the area between two graphs. How can I find that? Well, it's really quite simple. I simply need to look at the area between the top boundary coming from f of x and the x-axis. Let's make that blue. So that'll be this area over here. Blue area. That's going to be the integral a to b of my f function. And then I can look at the area under g. Let's make that pink. It's going to be over here. That's a to b with my g function as the function. And I simply need to take that away from the blue area. Take it away. So the area between two graphs will be calculated like this. But I can certainly put these together by reversing the sum difference property and merge them to integral a to b f of x minus g of x. And x is my variable. This is always going to be top boundary minus bottom boundary. So that means that it is beneficial to be able to graph it and visualize what's happening. Let's do a simple example first. Just make our own example where I'm going to look at the area, and again total area for sure, between y equal to let's make it fairly simple. Let's just say y equals x and y equals, let's pick something well below that. Let's pick something like x squared minus 2. And let's just go from 0 to 1. Let's visualize that first. So for my first example, I picked something fairly easy. I have my straight line y equals x. Y equals x. And then I have my parabola that I shifted down a little bit over here, like so. So this is y equals x squared minus 2, and 2 is over there. And I'm looking from 0 to 1. 1's going to sit over here. So this is my area that I'm interested in. Now the interesting thing is that I don't care about where these two graphs sit in relation to each other, is all I care about. Where they sit in relation to the x-axis is actually quite irrelevant. So initially it bothers people that, ooh, some of that area is below the x-axis. No, it doesn't actually matter in this case. Because the integral that I set up is the top boundary minus the bottom boundary. These could all be negative or positive or around the x-axis. If I set up top minus bottom, inside the integral is really a difference function, which is always going to be positive. Because I'm not looking at the x-axis now. I'm looking at the gap between the two, and if it's top minus bottom, then that gap is always positive. So the area is the integral, 0 to 1. X is the top minus x squared minus 2, which I have to put in brackets because it's the whole top minus the whole bottom. Then it's certainly a good idea to simplify this first, perhaps. X minus x squared plus 2. To just see what do I really have as an integral here. It's not a complicated one. I get a half x squared minus a third x cubed plus 2x, and I have to plug in 0 and 1, 0 making it very convenient, and I really just have to plug in 1. But it's always the same definite integral calculation. Let's quickly do that. And we get 2.17, let's say, as our area. So straightforward. I just have to somehow know which one goes at the top and which one goes at the bottom. That is perhaps the little bit of a snag, in that visualizing and by way of graphing them would seemingly help me figure out how to set up this integral now. But let me demonstrate something that makes this actually quite simple. Let's suppose these two functions in question were much more complicated, to the point where graphing them to figure out which one goes at the top, which one goes at the bottom, and how, and everything is just too much. Too much effort. It's not necessary. You're not being asked to graph it. You just want to find the area. What if we swap them around? So we know we have to set up the integral 0 to 1. That's in the question. What if I said, man, I have no idea how to graph these. I'm just going to guess. And guess a top, and then guess a bottom. And let's see what happens if I happen to guess wrong. This is now the wrong way around, right? I put the bottom first, but it has to be top minus bottom. So in a more complicated situation where I don't know how what the graphs look like, how they behave, I'm just going to guess. Let's see what happens there. Well, then I'm still going to simplify this first to see what integral do I really have. Okay, not much there. Then I'm going to do my antiderivatives. I'm going to get a third x cubed minus 2x minus a half x squared. And all of that needs to be calculated at 0 and at 1. So then I'm going to plug in 1, calculate, plug in 0, calculate. So let's do that. And I get negative 2.17 if I round. So now if I compare the previous answer, which is correct, to this answer, which is technically not correct, I notice something very handy in that the size of the number is the same. And that's always going to be the case. This guy is just negative when I swap them around. So if this happens, I can then simply say, oh, the area is, just drop the negative, 2.17. So it's actually much safer than it seems originally, in that I'm not reliant on the graph. If I don't know what the graphs look like, I don't know how they sit in relation to each other, I could just guess. Pick a top, pick a bottom. And if my answer comes out negative, the size of that answer is still correct. And I just drop the negative and say, that's my answer. So you really don't have to put much thought into which one goes at the top, which one goes at the bottom. Though it is nice to visualize, it is not necessary to find the answer. I can always use a graphing tool to graph both of them or whatever, but it's not necessary to rely on the graph in any way. So now let's just have a look at this. This was made simple for me because of the given interval 0 to 1. But what if I had the same, let's pick the same functions, same graphs, but a different interval. So for example, let's say we are looking for our area between y equals x and y equals x squared minus 2, I believe it was. And now let's say on, let's go 0 to make the calculations easy. And let's go 0 to, I don't know, let's go 10. So my graphs are still the same, but let's just see in general first, because I don't want to rely on this graph, right? Let's just say in general, what else could happen? Well, what could happen is I could have a graph for my one function, and I could have a graph for my other function, not f again. Let's say g. And let's suppose my interval is over here, a to b. I'm interested in calculating this area, which I can certainly visualize. But if I now set up a to b, top minus bottom, whichever one I pick, it really doesn't even matter, right? We've seen it doesn't matter. have to pick one though. Let's pick this one. If I stick to this, then top minus bottom, f minus g is going to be positive when f is actually the top. But when they cross each other, the top becomes the bottom, bottom becomes the top, and if I stick to this one integral, the other region, the other area is going to be a negative area. And these all get put together inside this one definite integral, and I'm going to have a cancellation effect again. So if they cross each other, I have the same kind of issue as before. Before, the other graph was the x-axis, and the graph crossing the x-axis was essentially the same as this. This is now just a little bit more general. So what do I need to do? I need to split it up wherever they intersect. So split up at the intersection C. However many intersections there are, right? If it crosses again, just like if it crosses the x-axis multiple times, I have to split it up across all of them to avoid this cancellation little trap that is waiting for me in a single definite integral. Which means that if I now go to my functions in the example, I need to always check, do they intersect, and are any of those intersection points in my given interval? So let's do that. So now I have to first find the intersection, if it even happens, right? So that means I set them equal to each other, x squared minus 2. Those were my two functions. And that means I have to solve x squared minus x minus 2. Now I can try and factor this and maybe have a look. I don't know what to do, so I always have my quadratic formula to quickly enough, simply enough, do that for me. So it's negative b, so negative 1. I'll just write it out so we can remember the quadratic formula for practice. Negative b, which is this coefficient of x, plus or minus the square root of b squared minus 4 times a times c. That's all in the square root over 2 times a. Now this simplifies a lot. Before I worry about the calculation, x equals 1 plus or minus. I like to figure out what's in the square root first so the calculation doesn't get too messy. I have a 1 and I have a plus 8. So 9 over 2. Did I pick a really nice one? Wow, that's nice. So that means it's 1 plus or minus 3 over 2, which means I have x with plus, let's say, which is 2, or x with minus. Oh, this is very convenient. I'm surprised. I just randomly made this up. 1 minus 3 is negative 2, so negative 1. So this guy is inside the interval that is given. So if I were to graph them, they cross over, let's just pick the previous example we have, they cross inside my 0 to 10 interval. And I'm now looking for this area and this area. And I don't have a top staying at the top and the bottom staying the bottom. They switch places, which means I need to switch as well. or at least I need to separate the integral. I think we can do it here. So that means I need to go 0 to 2, and I need to go 2 to 10. Now, it does help that I pick the right one. 0 to 2 will have x at the top, and x squared minus 2 at the bottom. And then they swap, x squared minus 2 minus x. The bottom becomes the top becomes the bottom. So I have these two. Now, the inside doesn't look quite the same, unfortunately. Let's see if we can do it in one line, though. X minus x squared plus 2 dx. So that'll be a half x squared minus a third x cubed plus 2x. And I have to plug in 0 to 2. Which we'll do in a second. Then for the other one, actually let's do it. Let's do the calculation. Let's finish one line. The 0 helps a lot, so it does make the calculation faster. Let's calculate that top one. Or did we perhaps do that already? I don't know. Let's just see. It's a new question. Let's do it again. We may have done this before, doesn't matter. 3.33. Now for the second one here, I have the integral 2 to 10 x squared minus 2 minus x. So let's go here, and let's say then 1/3 x cubed minus 2x minus a half x squared, and that has to be evaluated 2 to 10. So I have to plug in a 10 minus plug in a 2. So let's do that. Now I can't very quickly use the top line because the exact way the function looks isn't the same. So I just have to calculate it from scratch to be safe. All right, we get a lot because the parabola grows so fast, right? So that second part of the area over here is really big, actually, up here. So we get 266.67. So then I can say my total area is 270. Now these are both positive because we correctly changed which one was at the top and which one was at the bottom. But I do want to highlight one thing. Remember, we got our 3.33. Let's put that on the side. And I'm just going to erase this top one. I'm going to erase it completely. Well, not completely, but almost completely. Let's go back to my pen. Let's suppose we know the two functions in question, but and we understand that we have to split it up around 2, but we don't know what the graphs look like. We don't know which one is at the top and which one is at the bottom. We know that they're going to switch places, but we don't know how, and we don't want to go through the effort of figuring it out. I apologize if there's background noise. There's a little bit renovations going on upstairs. Let's suppose I don't know the order, right? I'm just going to pick the same for both. I'm going to pick x squared minus 2 at the top and x at the bottom. I know I'm going to be right in one of them and wrong in the other. But if I swap them and swap them again, both could be wrong. I have no idea. If these functions are more complicated, I don't know which one's at the top. I know they switch roles, but I don't know which one's right. So now I know one of these won't be right. But let's just keep going and see how wrong am I really going to be. So I have my integral 0 to 2, x squared minus 2 minus x. Yes, it looks the same as the second one. And so I have 1/3 x cubed minus 2x minus 1/2 x squared. And I have to plug in 0 to 2. What am I going to get? Let's do that. It shouldn't come as a big shock that I get negative 3.33. So that again means that I don't need to rely on my graphs. I don't need them. I can guess which one's at the top, which one's at the bottom, and if I guess wrong at any stage, the size of the number will be the same. I'm simply going to ignore that sign. If it's a minus, the size is still correct, and I just add them up. And it has the benefit that I now have the same looking expression inside my integral, which means the antiderivatives are the same, and everything is a little less work. Just to have that negative there, that's not a big price to pay at all. Let's do one more example. Okay, let's see. Area between two graphs. Let's pick something that I do not want to graph. I don't want to spend time on it. I don't care at all. Let's pick let's pick number 10. I like number 10. 10 is nice. I know it's not super complicated, but it's different. E to the negative x, e to the x, negative 1 to 2. Where's my drawing? So number 10, I have y equals e to the negative x, y equals e to the x on negative 1 to 2. All right, now I don't want to graph them. I don't want to look at them. I don't know anything. I need to find my intersections. See if these two functions intersect each other in the interval. So that means I set them equal to each other. Now this is a different looking equation for sure, exponential equation. What do I do to try and solve that? Well, it's much easier than it looks. Because this negative exponent, I could see it as 1 over e to the x, perhaps. Perhaps you would do that. And then I just have to multiply throughout by e to the x to get 1 equals e to the x, everything squared, which would mean e to the 2x. So let me just rewrite this. E to the 2x equals 1. So that means 2x has to equal 0, so x equals 0. And I see, whoops, that is inside my interval, which means I need to split it up. So I'm going a little fast perhaps, but you can always pause the video and double check stuff. So I need to split it up. -1 to 0. I don't know which one should be at the top. I'm just going to pick whichever one I want, minus the other one. And then I set up 0 to 2. I don't care which one goes where. One of them's right, one of them's not. Who knows? I know that only the sign of the answer will be wrong, not the size of the answer. All right, so antiderivative of e to the x is e to the x. Antiderivative of negative e to the negative x is going to be, well, let's suppose I'm a little uncomfortable with these. I leave the negative out of it. I won't put a dot there. I'll put a bracket there. E to the negative x. Yeah, it's a little chain rule, but it's so simple that I could just manually do it. It has to be e to the negative x with a negative in front. So it's really a plus there then. And I have to put in -1 to 0. Because I kept them the same, this antiderivative is going to be the same. I just have to plug in different numbers. All right. So e to the x plus e to the negative x. Let's do that. I get, oopsie line, what do I get here? -1.0862-ish. And then for my second one, let's do that. And we get 5.5244-ish. So I see, oh, I made a mistake in the order of the first one. Just drop the negative. So then the total area, I rounded these, and you can certainly use the originals, 1.0862 plus 5.5244. And we finish our question. So I don't need to see the graph. I don't need to have the right order of which one's the top and which one's the bottom. But what I do need is to split it up according to the intersections that fall inside the given interval. That I cannot skip. So let us quickly talk about one more. To just perfectly wrap this up, you'll see in some, let me zoom out here. You'll see in some of these questions, like number 5, that there's no interval given. There's no interval given. Why not? X squared and 2x. Y equals x squared. Y equals 2x. No intervals given. Let's see what these graphs look like. Well, I have my x squared graph, my parabola over here, and I have 2x, which is a straight line. So I have y equals x squared, y equals 2x, and you see that there's an area enclosed because these graphs intersect each other twice. So when there's no interval given, the interval is the two intersection points. So regardless, I still need to find the intersections by setting them equal to each other. And that is x squared minus 2x equal to 0. Factor out an x to get x minus 2 is the other one. So x is 0, x is 2. So from 0 to 2. So it's nice to visualize this for sure, and if they're simple graphs, we can certainly do that. And this is now the interval. That means the interval is 0 to 2. And I can set it up to go from 0 to 2. There's nothing in between. That's a crossing. I have the graph, so I might as well set them up correctly, but I know that's not a big deal if I happen to swap them around. I have x squared as an antiderivative minus a third x cubed. 0 to 2. Let us calculate that as our last example. And I get 1.33, which is already positive. If I happen to not have the graph, I picked the wrong one for the top, I would just get negative 1.33 and then say, oh, that's my answer is 1.33, not a problem. So in cases where I don't see an interval in the question, the interval is specified by the intersection points. So that wraps up our chapter on antiderivatives, integrals, definite integrals, and areas. We have one more topic left,